Hi, good morning, everybody. Remember, there's only 3 more shopping days till Halloween. And don't forget to show up on Wednesday. This will be really sweet. Hi, last Wednesday I was talking about molarity. Remember, we're talking about solutions. Anybody happen to think when you were passing a gas station that they were selling solutions? Different grades of gas are different solutions of gasoline or various components. And it's a solution. Now, when we talk about solutions, how do you standardize or make sure you always make the same solution? We call that concentration. And last Wednesday I started talking about, we did some work, about molarity. And molarity is defined as moles per liter, but in real life, in a lab, because 1 liter equals 1,000 milliliters, molarity is also defined as moles of a solute per 1,000 milliliters. And before I forget, start around. And therefore, how do we show that? Well, not with a dead marker. Molarity is moles of solute per 1,000 milliliters. And if you see that, what does that mean? Capital M in chemistry tells you molarity. Therefore, what does this mean? 1.66 moles, here's the solute sodium chloride, per 1,000 milliliters. And that's what that means. Since you know Dr. White likes to share, what does this mean? And the question I'm asking, what does that mean? I'll give you 2.876 seconds. Didn't know I could accurately time things that well. I can't. Alright, let's take a look. What does this mean? As soon as you see capital M, you know molarity, which is moles per 1,000 milliliters. Therefore, what this means is 2.51 times 10 to the 4th moles of HCl per 1,000 milliliters. Well, let's do one more. These are fun. This is going to be a fun week. Halloween's coming. Now why don't you try this one? What does that mean and what is the solvent? All right, I think everybody's done. Let's take a look at this. Capital M tells me molarity. Therefore, this is 3.75 moles, and this is sulfuric acid, H2SO4, per 1,000 milliliters. And this tells me, AQ in a bracket, tells me the solvent is aqueous, or this is an aqueous solution, and the solvent is water. And that's how you use molarity in terms of identifying solutions. Now, let's use molarity in the real world. That's where it's fun. There are various molarity questions. I just did a little review, which always helps. All right. It's time to play that game. What did Dr. White write on the board? No, I'll decode this. Let's look at the following. Question is, how many moles of HCl are in 532 milliliters of a 1.62 capital M HCl solution? Any time to write it down, then I'll do it, then I'm going to let you try one, because I share. All right, I think everybody has it down. So let's take a look at this. What are we being asked to find? Moles of HCl. What are we given? How many milliliters of solution? And we're given this number. And at this point, I like to say, ooh, capital M, I know what that is. That's molarity. And what does this mean? This means 1.62 moles of HCl per 1,000 milliliters. And now there's really one main number I have to start with, which is the milliliters of the solution. And if I can convert this in one step using some ratio, what units am I trying to get to? Well, I want to get to moles of HCl. And now, what do? Because you haven't thought about this for a while. It's time to use your good buddy, your good friend, unit analysis. Whatever you're trying to get to, units go on top. Whenever I'm trying to get rid of, the units go below, underneath the ratio, or in the bottom. And where do I get that number? From the molarity. How many moles per 1,000 milliliters? In this case, it's 1.62 per 1,000 milliliters. Before I go ahead, I'll check my units. Notice milliliters divided by milliliters comes number 1, cancel out. I'm left with moles of HCl. I'm on the right track. And now I'll go over to my calculator. My calculator gives me this number on test 3, as in test 2 and 1, we'll say please use proper significant figures for all calculated answers. If we look at this, 3 significant, 3, I'm in my right again, exact number, rounding that off to 3, that would be 0.862 moles of HCl. And that's how you do it. And since you know I'm going to share, I better. First of all, any questions? I haven't said this in a long time, but remember in my class, in my world, anywhere around me, there's no such thing as a dumb question ever. Speaking about questions, yesterday one of your colleagues sent me an email, actually last night I answered this morning, inquiring about test 3. First of all, good news, we're on schedule, right on schedule. And test 3 will be a week from this Wednesday. We'll finish up solutions probably today or Wednesday. On Friday, and I'll remind you again on Wednesday, we'll go through the solutions problem set. So we're pretty much on track and we're going at a good pace, hopefully for you to do well, which is what I like to do. And why don't you try this one? And the question is, how many moles sodium fluoride are in 322.2 milliliters of a 7.112 capital M NaF sodium fluoride solution? As you finish early, think about what Halloween costume you'll be wearing. Or what Halloween costume Dr. White might be wearing. And coming as an organic chemist. Oh wait, I am. All right, let's get it going. Let's take a look at this problem. I think everybody's about done. Anybody need more time? Going once, twice? Let's do it. What are we being asked to find? How many moles of sodium fluoride? What are we given? A volume. How do you know it's volume? Milliliters. ml, milliliters, volume. We're given this number too. I look at that and I see capital M. Capital M tells me molarity. Molarity, moles per 1,000 milliliters. And immediately I'll ask myself, what does that mean? I know molarity, 7.112 moles sodium fluoride for 1,000 milliliters. And now the real number we really have to start with is this. And what are we trying to go to? Moles sodium fluoride. And if we take this, we look at this, and it's time to use unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. Where do I get the numbers? Because I knew capital M molarity means moles per 1,000 milliliters, and therefore I can put in here 7.112, 1,000. Milliliters cancel out, I'm left with the right units, I'm on the right track. And now go to my calculator. Someone close the door, please. Do that thing. If I can hear it, you people can hear it even better. Don't be shy. And this is the number we get. Now, if we look at this, this is 4 significant figures, 4 exact number. My answer should have 4. How do we round that off to 4? Keep 2, keep 2, keep the 9, keep the 1 for now. And the round off number is 4. It's 4 or less. I dropped that. And the correct answer here is 2.291. And that's how you do. Oh, let's do one more. Why don't you try this one? And let me read it. How many milliliters of a 3.46 capital M KBr solution must I use to get 2.17 moles KBr? Why don't you try that? And remember, use your good friend, your good buddy, unit analysis. I skipped question 2, which I rarely put on the test. I've gone to number 3 on the slide. Better yet, I'll get to this in a second. Remember, when you're done, look up and smile. I think everybody's done. Let's take a look at this. And the question is, how many milliliters of I have this number, 3.46 capital M KBr, potassium bromide solution, must I use or measure out to get 2.17 moles KBr? So what do we really have to work with? This right here, I have 2.17 moles KBr. What am I trying to get to? And the answer is, I'm trying to get to milliliters. And now I'll use unit analysis again. Whatever I'm trying to get to, I'll put on top. Whatever I'm trying to get rid of, I'll put underneath this ratio. And where do I get these numbers? Oh, wait, capital M, molarity. What does this mean? This means 3.46 moles KBr per 1,000 milliliters. And let me remind you, I've got room over here. If you have one thing equal another, or if you have a ratio like this, well, let me not do it that way. That's not the right way to do it. Let's just go ahead. And if you have this, where do I get those numbers? 1,000 milliliters per 3.46 moles KBr. And now, if I look at my units, moles KBr divided by moles KBr cancel out, and I'm left with milliliters, so I'm on the right track. And now, I'll go to my calculator. And this is a 2. Now that looks better. And here's the number my calculator gives me. And I have 3 significant figures, exact number 3, round that off to 3 significant figures, and I have 627. And that's the beauty of molarity. You make up stock solutions, and when you need a certain amount of moles of something from that stock solution, you just measure it out. You calculate it, go to the graduated cylinder, measure out 627 milliliters, and you've got your moles of KBr. Question?
Why wasn't it 3.46 as the first mole? Why was it 2.17? Because the whole time, whenever you get a capital M, you've been making that the first.
And why is it switched, one on top, one underneath?
No,
All right, oh, why did I start with moles?
no.
Which one?
Why did you
write it
start
wrong?
with 2.17 mole and not 3.46 mole for both moles?
All right, because this is what we're given, okay?
You were given the 3.46 as well.
No, we're saying how many moles of KBr? Look at the units, okay? This is a slightly different question than the one before. Here we're given moles, we're given molarity, we're trying to find milliliters. So this is what we start with. And then this is what we're trying to get to, okay? Now this is different. In the past I had moles on top and milliliters underneath. But that's not what you're starting with, and you use the unit analysis as your guide because it helps you determine what that ratio is. Does that help? Okay. And thank you for your question. All right, now, when you're using molar solutions, you have a stock of them, and how do you make them? Well, let's do it the following. And the real thing to do is figure out how to make these solutions. And if we look at this, this is a little different. And the question here is, you're trying to make one of these solutions. And here, how many moles of HF, hydrofluoric acid, are needed to make 633 milliliters of a 1.723 capital M HF solution. Oh, by the way, for those who aren't familiar, hydrofluoric acid is one of the most dangerous chemicals around. It's the only acid that will etch glass. And that's what they use to etch glass when you see etched glass somewhere, like somebody's name in there. The dangerous part of HF is if you get it on your skin, it will eat all the way to your bone. And it's the only time in my whole chemical career I ever refused to work on a project. When I was at one company, the research director came to me and asked me, I work on this project with HF. I told him no. He looked at me, 1 second, and I'll get to you in a second, Angela. But anyways, he asked me again. I said, I think it's time for me to get my resume out and look around. And because I had made a lot of money for the company, he said, no, you don't have to do that, I'll find someone else. He found someone else, and that person literally had a nervous breakdown working with this chemical, because whenever he did do any reactions, he was in a hazmat suit with an air tank, and standing right behind him was a technician dressed similarly, just to watch him, so if there were any problems, she could run and get help. And he never had any problems, but it was played quite a toll on him. And at that point, I thought afterward, thank goodness I had the courage to say no. But anyways, then the project was dropped. You had a question about it?
Yeah. If the HF goes through your skin, wouldn't it go through the suit too?
Through the what?
Through the suit that the people have to wear, so it doesn't touch your
There's
skin.
certain things it does not react with.
Oh,
All right.
okay.
Certain acids in particular will not attack certain types of rubber like neoprene?
Oh, okay.
And that's a good question.
Because when you said it goes through
Well,
your skin, I was like,
Well, your skin is, and I won't teach in this, well, I will get a little into organic chemistry, but your skin you don't think of is a chemical. And it's a different chemical than, say, a rubber glove or those suits. And therefore, the chemistry of that, how it reacts is different. Otherwise, well, we'd have problems. Just like I said, HF will react with glass, but every other acid you buy in glass bottles. HF comes in plastic because plastic won't react with it. Now, one time in high school, and I cannot say I was the person who did this, but when I was in high school, we had a thing called science seminar. Never try what I can tell you. And a student took some HF, put it in a squirt gun, which is plastic, and went to a couple friends he didn't like and sort of etched things in their car windows. Never get a chemist mad at you. But anyways, HF won't react with everything, but it will react with your skin. Other acids will react with your skin too, but not as bad. All right, let's get back to this. We're talking about molarity, and the question is, how many moles of HF? So immediately we know, what are we trying to find? Moles of HF are needed to make what? 633 milliliters of a solution. And what is that solution? .732 capital M HCl. As soon as you see the capital M, what do? You say, I know that. That means molarity. Well, you don't have to say that, but you should think it at least. And what does that mean? And this is an important part you should be able to do. Molarity means moles per liter. In this case, 1.732 moles of HCl per 1,000 milliliters. And now, if I look at this, this is the key number I start with. What units am I trying to get to? Trying to get the moles of HF. Now I'll use unit analysis. What I'm trying to get to, I'll put on top of the ratio. When I'm trying to get rid of the units, I'll put down there. Where do I get those numbers? From knowing this, molarity means moles per 1,000 milliliters. And 1,000 milliliters goes here. Milliliters divided by milliliters becomes the number 1, cancels out, and I'm left with the right units. So now I can go to my calculator. And this is the number I get. And now if I look at it, I'll say 3 significant, exact number, 4 significant. How many significant figures should your answer have? Remember, when you're doing a multiplication, you have the same number of significant figures as the number with the fewest, and division too, that has the fewest significant figures. 3, 4, exact number. Round that off to 3 significant figures, and that would be this number, and that's how you do it. Let's go to a safer chemical. Yes, Ingrid?
Why don't you use, why don't you count 633 milliliters as like a whole number, whatever you called it?
What?
Like, why don't you use that as an
Call it a
exact
whole number?
Or exact number.
Because it's an exact number, because it's measured.
Okay.
Whenever you have a volume, it's measured. Example, hold on. real life. On here, when it was full, it says 700 milliliters. That's an exact number, one significant figure. The zeros at the end aren't. But when you measure, when you see a number like that, that's a measurement. When you see 1,000, this is a very good question you asked, thank you. And when you see 1,000, that's part of the definition. Molarity, moles per 1,000 milliliters, and that 1,000 is defined. So that's why that's an exact number. But volume or other things you can measure, like moles, how many moles of something, you calculate, measure that. Those are always significant figures, how many, never exact. How many people in this room are exact, because you can't have half a person who's alive. Does that help?
Yeah.
Good. And now you won't get that wrong on the test, too, which is a good thing. All right, let's take a look at this. And I got the number up there, so it's time for me to let you try one. And I said I'd work with something safer, so let's go real safe. And why don't you try this one? How many moles sugar is a chemical, you tend to forget that, but it is, are needed to make 511.2 milliliters of a 2.113 capital M sugar solution? And why don't you try that? Chemistry, it's not bad. I should have said bad. It's even fun. Well, looks like everybody's done. Let's do this. But first, a commercial from Dr. White. Don't forget, I'm available 24/7 on YouTube, and you can see my lectures. Don't forget to tell your friends, neighbors, and loved ones. If I can get 100,000 views or more, I might make some money. Not good, but that would be awesome. I could start my own Dr. White YouTube fan club. All right, let's take a look at this. How many moles of sugar that's what we're trying to find. Boy, this is a sweet problem. Look out, it's Bad Humor Monday. are needed to make 511.2 milliliters of a 2.113 capital M sugar solution. And I look at that and I see capital M. I know what that means. Molarity. Molarity. Moles per liter or moles per 1,000 milliliters. What this really means is .113 moles of sugar per 1,000 milliliters. That's better. And now what do I have to start with? This. If I can take and convert this question. What? Ah, got an extra one. Thank you. I'm seeing triple. That was a problem I meant to put on the test. All right, thank you. We have the right number, and that happens in real life. You make a mistake like that. This is how many milliliters we have. What are we trying to get to unit-wise? Moles of sugar. I got that one right. And now use unit analysis. Whatever you're trying to get to, you put the units on top of this ratio. Whatever I'm trying to get rid of, milliliters, I'll put underneath. And where do I get those numbers? From knowing capital M, molarity is 2.113 moles of sugar per 1,000 milliliters. And therefore, keep an eye on me because I already made one mistake today. Did I get that right? Count the zeros too. It was actually the pen swallowed that pen. And now, before I pick up my calculator, this is always important, you should do on your test. Check your units so they cancel out and you end up really with moles of sugar. Milliliters divided by milliliters becomes number one. I'm left with moles of sugar. I know I'm on the right track. And therefore, I'll come over here. Got it right this time. And this is the answer my calculator gives me. Notice 4 significant figures, 4 significant figures, exact number. How do you round that off to 4 significant figures? Keep the 1, keep the 0, keep the 8. Should keep the 0. Let's look. That's the 4 significant figure. Use the 1 to round off. That's 4 or less. So the answer here would be 1.080 moles of sugar. And that's how many moles of sugar I would have to mix with that amount of water to make that molarity solution. But in real life, I've never seen a balance that measures out moles. What do balances measure out? Weight, grams. So let's look at the real life question. Amazing how you get your attention real quick. And all right, let's take a look at this question. And this is real life. When you're making molar solutions, How many grams sodium chloride are needed to make 832 milliliters of a 2.37 capital M molar sodium chloride solution? So let's take a look at this. First question is, what are you being asked to find? And the answer is, how many grams of sodium chloride? What are you given? Well, how many milliliters of solution we want to make? What also are we given? This number, 2.37 capital M NaCl solution. And, I'll wait until you finish writing. Let's try something different. When you're done, look up and make a funny face. All right, everybody got this copy? I'm going to write something on the board right now. Do not copy it down. Well, I say, what do I have to start with? I have this. What units am I trying to get to? Again, don't copy this down. And now I use the unit analysis, and that tells me whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And now I look for those numbers to fill in there, and I'm stuck. Nowhere on this board do I have a ratio, or can I find a ratio of grams to NaCl to milliliters. What do? Here's what you do. I know I can go from milliliters to moles. And I know I can always go from moles to grams. This is a two-step problem. And now I can go to what I'm trying to get to, because otherwise there's no way I can get to it in one step. So let's do step one. And here, this looks familiar. What do I have to start with? This number. What am I trying to get to? Well, in step one, I want to get to moles of whatever I'm trying to find, in this case, sodium chloride. And now I'll use unit analysis to say, well, I'm trying to get to moles of sodium chloride. I'll put that on top. I'm trying to get rid of milliliters. I'll put that underneath. And where do I get that number? Oh, wait, capital M, molarity. What does this mean? 2.37 moles sodium chloride per 1,000 milliliters. So now I can put in the 2.37, 1,000, and they got a lousy looking zero there, so let me improve upon it. And now look, milliliters divided by milliliters cancel out. I'm left with moles, so I'm going to go to my calculator. And this is a number. Now, this is one of those problems you can round off at the end or each step. I'm an each step person. 3 exact number, 3 significant figures. Now, this gives me moles of sodium chloride. but I want to get to grams of sodium chloride, so now I'll do step number 2. And here, what do I want to do? I want to go for moles. In this case, I have 1.97 moles. Let me say something about it. That's better. Hold on 1 second. That's better. And what do I want to get to? Grams of sodium chloride. What do I do? Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Where do I get that? On test number 3, like test 2, it will say remind you, 1 mole of a compound equals its molecular weight. The molecular weight is the sum of all atomic weights. So now I'm going to, in your case, you'll turn to the last page, but in my case, I'll go out to the internet. Go to the dynamic periodic table. And now what do we need? Sodium chloride. One sodium, 1 chlorine. Remember, like test 2 will say, please use 3 significant figures for all atomic weights. Sodium is 23.0. We go over to chlorine. The 3 significant figures is 35.5. Add it up, and we have 58.5, and 1 mole, 58.5 grams. And now, before I pick up my calculator, I will look at this and say, do my units cancel out? And moles divided by moles, sure does. I'm left with grams sodium chloride. Looks good. And now, go to my calculator. And this is one of those cases, I'm going to roll this semester, where both ways come up with the same answer. This is 3. You should end up with 3 significant figures. 1 is an exact number. I round that off to 3 significant figures. That's 115 grams. So what this tells me is, if I take 115 grams and mix it with this amount of, in this case, let's say the solvent is water, I will make this molar solution. And that's how we make stock solutions. And now you also see why it's 10 points, because it's more work. Any questions? Remember, you need 2 steps, because there's no way I can go from milliliters to grams in 1 step. And why don't you try this one for your fun and enjoyment on this sunny day. I don't know if you saw the forecast for Halloween, but they're talking about rain and snow. Global warming.
Do you think you can go to the periodic table?
Oh, I'm sorry. I thought you memorized these by now. Thank you very much, John. It's the bad thing about being a chemist for a while. I guess I have been. You assume everybody else knows these standard things. Like, what's the number that comes after 9? Well, everybody knows 10. And what's the atomic weight of hydrogen chlorine? Well, everybody should know that. No. There you go. I think everybody's done. Let's do this. And the question is, what are we being asked to find? We're being asked to find how many grams hydrochloric acid. By the way, hydrochloric acid, though dangerous, is a lot safer to work with HF. I've worked with it many times. And what are we given? We're trying to make 345 milliliters of this 0.461 capital M HCl solution. As soon as I see the capital M, part of my brain says, I know what that means, I know what that means, I'm going to write it down. And I do. This means molarity, 0.461 moles HCl per 1,000 milliliters. And now, I look and I say, there's no way I can go from milliliters to grams. This takes 2 steps. First step, milliliters to moles. Second step, moles to grams. So let's do step 1. I have how many milliliters? 345 milliliters. And I'm trying to get to moles. In this case, it's HCl. I'm going to use unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get, sometimes my grandmother trained me well. Whatever I'm trying to get rid of goes underneath. And where do I get those numbers? From molarity, capital M, moles per 1,000 milliliters. So in this case, that's 0.461 per 1,000 milliliters. Milliliters cancel out, I'm left with moles. I now come over here, I do common mistakes students make on test 3. Instead of putting in 1,000, they put in 100. Make sure there's 1,000 there. And this is the number I get. Now notice I'm backing by three exact numbers, significant figures. So if I round it off at this time, I'll do 1.59 moles. And now I'm ready for step 2. And that's going from moles, HCl, and I want to get to my final answer right here, grams of HCl. I'll use unit analysis again. You may have any nightmares here. You say, use unit analysis, you're good buddy, you're good, Halloween's coming up. Anyways, whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of, the units go underneath of the ratio. Where do I get these numbers? 1 mole of a compound equals its molecular weight. The molecular weight is the sum of all atomic weights. I have an HCl, a hydrogen, a chlorine, and this is 101 for one of them, 35.5. Add that up, 36.51. Remember, when you're doing an addition, you get the same number of significant figures past the decimal as the number that has the fewest significant figures past the decimal. This has 2, this has 1, the answer should be 1 past the decimal. Keep the 5, use the 1 to round off. Drop that. For every 1 mole, 36.5 grams. And now I'll go back to my calculator. And lo and behold, I'm still on a winning streak. No, actually it's different. This is different. If we round these off to 3 significant figures, this becomes 5.81 grams. This is 5.80. Either way on my test would be correct. I didn't have this formatted to 3 significant figures. That's why the 0 disappeared. And that's how you do it. Let's remind you again what we had to do here. And if we look here, you cannot go from milliliters to grams. It takes 2 steps. The first step, we go from milliliters to moles using unit analysis, which we practiced today. And the second step, which you learned for test 2, but we also practiced today, is going from moles to grams. Any questions? With that, I finished everything for the chapters that are on test 3. Now, the important thing I was thinking about it this morning, and I think because we're at a good place, on Wednesday, it's important you show up, it's always important you show up, but I'm going to go back and go over some key things you should know how to do for gases and also solutions. That'll help you for test 3. So you mostly do better than you did on test 2. But I've got time. Guess what time it is? It's new chapter time. And this new chapter is something we've already done 2 labs, but it's now time to learn about it in the class. This will be on test 4, not test number 3. And the name of this chapter is acids and bases. And the question is, what is an acid? What is a base? And at first glance you say, oh, Dr. White, you're just being silly. But the answer is no. For many years, this was a very difficult question to answer in chemistry. What is an acid? What is a base? All right, listen up. Do not write down what's on this page. Do not. But the first person to answer that question was the chemist Arrhenius, and his acid-base theory was an Arrhenius acid is a hydrogen-containing compound in water that produces hydrogen ions. And hydrogen ions we define as H+, a hydrogen with a plus charge on it. And an Arrhenius base is a molecule in water, a hydroxide. Hydroxide is OH-, containing compound that in water produces hydroxide. And says, see board for examples, so I better do that. An example of an Arrhenius acid would be hydrochloric acid. This is an acid. And another important acid, sulfuric acid. By the way, H2SO4, sulfuric acid, is the chemical that's made, the most widely made or highest production chemical in the United States annually, is this chemical because it's used in so many things in making things. Now, examples of a base. Sodium hydroxide, NaOH. Another base like this would be potassium hydroxide. And these are bases under the Arrhenius theory. But there's one problem with I'll come back to the naming in a little while and bases. There's one problem with the Arrhenius theory. What happens when you're not in water? And what happens when you don't have hydroxide in a molecule? What happens? Well, you can't do anything with the Arrhenius. And therefore, two chemists, Bronsted and Laurie, and you can see I forgot to do this morning earlier, so I'll do it right now real quick. Came up with a theory that explains acids and bases. Now, the importance of the Bronsted-Laurie theory was, and this was what made it difficult, is everything under Arrhenius that's an acid or base has to be an acid or base under Bronsted-Laurie. And they successfully did that, and seeing all of you are starting to get fidgety, I'll let you out a whole 40 seconds early. With that, I'll see you on Wednesday, and we'll go over some important stuff for test 3, so do show up. And also, I'll have a special surprise for you on Wednesday.
Can you?